Our planet's oceans are places of immense power and profound mystery. For centuries, sailors have navigated these vast blue expanses, learning their rhythms and respecting their might. They have come to understand the patterns of the tides, the behavior of the winds, and the nature of the waves that travel for thousands of miles across the surface. But every now and then the ocean does something utterly unexpected. Without warning, from a seemingly normal sea, a single colossal wave can rise up. This is no ordinary wave. It is a rogue wave, a vertical wall of water that can appear and disappear in moments, leaving behind only devastation and disbelief. These sudden giants are defined by their sheer extremity. Scientists classify a wave as a rogue if its height is more than double the significant wave height of the area. The significant wave height is the average height of the tallest one-third of the waves around it. So in a sea with waves averaging, say, 5 meters, a rogue wave would be a monster towering over 10 meters high. They are often described as holes in the sea, followed by a near-vertical wall of water. The force they carry is almost unimaginable, capable of exerting pressures of up to 100 tons per square meter, a force far beyond what most ships are engineered to endure. The danger of these waves lies not just in their size, but in their complete unpredictability. They are not part of a predictable weather system or a tsunami caused by an earthquake. They are statistical freaks, anomalies that erupt from the ocean's surface for reasons that we are only just beginning to comprehend. Imagine being on a ship sailing through what seems like a manageable storm, when suddenly a wave 3 or 4 times taller than any other rises before you. It is a fleeting event, lasting only a few seconds, but in that short time it can spell disaster for even the largest and most modern vessels navigating the world's oceans. Understanding these phenomena is a critical mission for scientists and engineers. For those who make their living on the water, rogue waves are a terrifying reality, a hidden danger that can turn a routine voyage into a fight for survival. By studying them, we learn more about the fundamental physics of our oceans and, crucially, how to protect the lives and the vessels that must cross them. The journey to understand these liquid mountains is a story of myth, science, and survival, showing us that even in our modern world, the ocean still holds secrets capable of astonishing and humbling us all. For hundreds of years, the existence of rogue waves was confined to the realm of maritime folklore. Seasoned sailors would return to port with harrowing tales of monstrous waves that had appeared from nowhere, walls of water that rose up and swallowed the sky. They spoke of ships being lifted and then dropped with such violence that their hulls would break, or of waves so steep that they would simply crash down onto a vessel, crushing it instantly. These stories were often shared in hushed tones, passed down from one generation of mariners to the next as cautionary tales about the untamable power of the sea. However, the scientific community remained deeply skeptical of these accounts. For a long time, the prevailing theories of how waves behave were based on linear models. These mathematical models suggested that waves in the open ocean simply could not combine to reach such extreme heights. According to the science of the day, a wave taller than about 9 or 10 meters or 30 feet was considered a physical impossibility. As a result, the stories from sailors were often dismissed. They were seen as exaggerations, the product of fear and imagination in the midst of a violent storm, or perhaps just sailors' tall tales told for effect. This disbelief was so widespread that even credible witnesses were met with ridicule. In the 19th century, the respected French naval officer and explorer Jules Dumont d'Urville reported encountering waves that he estimated to be over 30 meters high. His detailed report, coming from an experienced commander, was met not with scientific curiosity but with public scorn. The idea was simply too far outside the accepted understanding of ocean physics. The consensus was clear. The sailors were wrong and the mathematical models were right. The ocean, while powerful, was thought to behave within predictable limits. This official denial continued well into the 20th century, even as evidence mounted. Ships continued to disappear without a trace in unexplained circumstances, and survivors continued to tell their unbelievable stories. Between 1969 and 1994, an astonishing 22 supercarriers, massive cargo ships, were lost at sea. Many of these losses were blamed on rogue waves, resulting in the tragic deaths of over 500 people. Yet without concrete instrumental proof, the scientific world held firm. The ocean's greatest monsters remained, in the eyes of many, ghosts of the sea, products of myth rather than measurable fact. Everything changed on the first day of 1995. In the middle of the tempestuous North Sea, a storm was raging around the Draupner gas platform, a sturdy structure built to withstand the worst weather the ocean could throw at it. The platform was equipped with state-of-the-art instruments, including a downward-facing laser designed to precisely measure the height of the waves passing beneath it. Engineers had calculated that the maximum wave height the platform could possibly encounter, even on a 10,000-year basis, would be around 20 meters. The waves on that New Year's Day were already large, with a significant wave height of about 12 meters. Then, at 3:20 in the afternoon, the instruments recorded something extraordinary. A single colossal wave bore down on the platform. The laser measured its peak height at an incredible 25.6 meters, or about 84 feet. It was more than twice the height of the waves around it, and far exceeded the theoretical maximum that engineers believed was possible for that location. The wave struck the platform with immense force, causing minor damage, but crucially the platform held. And more importantly, its instruments had captured the first irrefutable scientific evidence that rogue waves were not myths. They were real. The recording of the Draupner wave, as it came to be known, sent shock waves through the scientific and maritime communities. It was the smoking gun, the concrete proof that had been missing for centuries. The data was undeniable. It showed a wave that was exceptionally tall, unusually steep, and had appeared from a sea of much smaller waves. This single event forced scientists to abandon their old linear models, which could not account for such an extreme event. It proved that the sailors' tales were not exaggerations. They were first-hand accounts of a very real and very dangerous oceanic phenomenon. The confirmation of the Draupner wave opened up a new and urgent field of oceanographic research. Scientists finally had a precise measurement of a rogue wave, a benchmark against which they could test new theories. The focus shifted from debating the existence of these waves to trying to understand how they form and how to predict them. The Draupner platform's laser had, in a single moment, transformed a sea monster from a legend into a scientific puzzle. A puzzle that, if solved, could help save ships and lives from the ocean's most surprising and terrifying creations. For 25 years, the Draupner wave stood as the benchmark for rogue wave extremity, but in November 2020, off the coast of Ucluelet, British Columbia, an even more remarkable event occurred. A sensor buoy floating in the Pacific Ocean recorded a wave that, while not as tall in absolute terms as the Draupner wave, was proportionally far more extreme. The wave measured 17.6 meters high, or about 58 feet. What made this wave so astounding was the sea state from which it emerged. The surrounding waves were only about 6 meters tall. This meant the Ucluelet wave was nearly 3 times the height of its neighbors. This incredible size difference makes the Ucluelet wave the most extreme rogue wave ever recorded in terms of its proportionality. While other waves have been taller, none have ever been observed to be so much larger than the waves immediately around them. Researchers who analyzed the data described it as a once-in-a-millennium event. It was a powerful reminder that even after decades of study, the ocean still has the capacity to produce events that defy our expectations and push the boundaries of what we thought was possible. The buoy that recorded it thankfully survived the encounter, giving us a precious new data point. The discovery of the Ucluelet wave highlights the importance of having monitoring equipment deployed across the world's oceans. These buoys act as our silent sentinels, patiently waiting to capture these fleeting rare events. Without that single buoy floating off the Canadian coast, this extraordinary wave would have passed by completely unnoticed, its existence known only to the sea itself. Each new recording like this provides invaluable information that helps scientists refine their models and better understand the conditions that can lead to the spontaneous generation of such monstrous walls of water. It shows us the true randomness and violence of these phenomena. This event also serves as a stark warning. A wave that is 3 times the height of the surrounding sea would be a terrifying sight for any vessel. It would appear as a sudden, sheer cliff of water, rising up without any warning from an otherwise manageable sea state. The forces it would exert could be catastrophic, even for large, well-built ships that might have been navigating the 6-meter waves with relative ease. The Ucluelet wave is a testament to the fact that the ocean's potential for sudden, localized violence is a constant and present danger lurking unseen beneath the waves. Beyond the scientific data, the true nature of rogue waves is best understood through the stories of those who have survived them. In 1995, just weeks after the Drapna wave was recorded, the magnificent cruise liner, the Queen Elizabeth II, was sailing through a hurricane in the North Atlantic. The ship was battling enormous 9-meter waves when, according to the captain, an immense wall of water appeared ahead. He later described it as looking like the White Cliffs of Dover. This rogue wave was estimated to be 27 meters or 90 feet tall. It struck the ship head-on, but miraculously the vessel rode up the face of the wave and survived, though passengers described a terrifying experience. Not all ships have been so fortunate. One of the most haunting stories is that of the MS München, a state-of-the-art German cargo ship. In December 1978, the ship was crossing the North Atlantic when it sent out a garbled distress signal and then vanished. An extensive search found only a few pieces of wreckage, including one of the ship's lifeboats. This lifeboat had been stowed 20 meters above the waterline. Yet the twisted steel hinges showed that it had been ripped from its place by an incredible force from above. Investigators concluded that only a massive rogue wave could have caused such damage, striking the ship with enough power to destroy it. Even the simplest of objects can tell a story of a rogue wave's power. In February 1997, the container ship Tokyo Express was hit by a wave so powerful it was described as a great wall of water. The ship tilted 60 degrees, losing 62 shipping containers into the sea off the coast of Cornwall, England. One of these containers was filled with nearly 5 million Lego pieces, many of them ironically sea-themed, like octopuses and flippers. For years afterwards, and even to this day, these plastic pieces have been washing up on the beaches of Cornwall, a quirky and constant reminder of the immense power that tossed a massive container ship like a toy. These accounts, from the terrifying survival on the Queen Elizabeth II to the tragic mystery of the MS München, paint a vivid picture of the sheer violence of a rogue wave encounter. They are not simply large waves, they are freak events that behave in ways that defy intuition. They can appear in storms or in relatively calm seas, and their impact is devastating. The stories of sailors and the wreckage they leave behind serve as the human testimony to the scientific data, grounding the abstract numbers in the chilling reality of what it means to face one of the ocean's hidden giants. Since the confirmation of the Drapna wave, scientists have been working tirelessly to understand the physical mechanisms that create these ocean monsters. While the exact causes are still a subject of intense research, Three main theories have emerged to explain how a rogue wave can suddenly form. The first and most straightforward theory is known as constructive interference. Imagine waves of different sizes and speeds traveling across the ocean from different directions. If by pure chance the crests of several of these waves align at the same point and at the same time, their energies combine. For a brief moment, they form one single extraordinarily large wave before dispersing again. A second, more complex theory involves the interaction between waves and powerful ocean currents. This is particularly relevant in specific areas of the world, like off the coast of South Africa. When waves generated by a storm travel against a strong, fast-moving current like the Agulhas current, something interesting happens. The current effectively squeezes the waves, shortening their frequency and causing them to bunch up. This stacking effect can force the waves to grow much taller and steeper than they would otherwise, creating the perfect conditions for a rogue wave to form. It's like a traffic jam on the ocean, where wave energy piles up. The third and perhaps most fascinating theory comes from the world of quantum physics and is known as nonlinear interaction. This idea suggests that, under certain conditions, a single wave can spontaneously steal energy from the smaller waves around it. It acts like a predator, feeding on the energy of its neighbors and growing rapidly in size at their expense. This process continues until the wave becomes incredibly large and unstable, at which point it collapses. This theory helps explain the observation that rogue waves are often preceded by a period of relative calm, as the surrounding waves have had their energy drained away. These three theories are not mutually exclusive. It is highly likely that rogue waves can be formed by a combination of these factors. The ocean is an incredibly complex system, and the formation of a rogue wave is probably the result of a perfect and terrifying storm of conditions. Whether it's a chance alignment of crests, a battle between wave and current, or a wave that cannibalizes its neighbors, the result is the same: a sudden, unpredictable monster rising from the deep. Understanding these processes is the key to one day being able to forecast where and when they might appear. While rogue waves can theoretically appear in any body of water, including the Great Lakes, certain parts of the world's oceans have earned a reputation as hotspots for these dangerous phenomena. These are areas where the unique combination of currents, weather patterns, and seafloor geography creates a more fertile breeding ground for giant waves. By studying these locations, scientists can learn more about the specific conditions that increase the likelihood of a rogue wave encounter, helping to create warning systems for some of the planet's busiest shipping lanes. One of the most notorious rogue wave hotspots is the ocean off the east coast of South Africa. This is the home of the Agulhas current, one of the fastest and most powerful ocean currents in the world. It flows southward, directly opposing the large waves that roll in from the Southern Ocean, which are generated by powerful storms near Antarctica. This direct opposition between a strong current and large waves creates a perfect scenario for the wave-current interaction theory. The resulting waves are notoriously large and steep, and this area is believed to have been responsible for damaging or sinking over 150 ships in recent decades. Another significant area of concern is the North Atlantic, particularly where the warm, fast-flowing Gulf Stream meets the colder waters of the north. This region is famous for its violent and unpredictable weather, especially during the winter months. The interaction of powerful Atlantic storm systems with the strong currents of the Gulf Stream can create chaotic sea states where rogue waves are more likely to form. Some researchers have suggested that this phenomenon could be a contributing factor to some of the unexplained disappearances within the area popularly known as the Bermuda Triangle, providing a scientific explanation for events once attributed to paranormal forces. Other areas of heightened risk include regions known for intense and persistent storms, such as the North Pacific and the waters around Cape Horn at the southern tip of South America. By mapping these hotspots and understanding the underlying oceanographic conditions, we can improve safety at sea. Shipping routes can be adjusted during high-risk weather patterns, and vessels can be designed to better withstand the specific types of waves found in these regions. Identifying these danger zones is a critical step in turning our knowledge of rogue waves into a practical tool for prevention and survival. When people think of enormous waves, they often picture the spectacular rideable giants seen at places like Nazar in Portugal, where surfers challenge mountains of water. However, it is crucial to understand that these famous big-wave surfing spots are fundamentally different from the rogue waves of the open ocean. The colossal waves at Nazar are predictable and are a result of very specific underwater geography. A deep underwater canyon, known as the Nazar Canyon, points directly at the shore. As massive ocean swells travel along this canyon, they are funneled and focused. When this deep water suddenly hits the much shallower continental shelf, the wave energy is forced upward, creating a towering, breakable wave. These surfing waves, while immense and dangerous, are expected. Surfers and safety teams know when the conditions are right for them to appear. They are the product of a known swell interacting with a known seafloor feature. Rogue waves, on the other hand, are defined by their shocking unpredictability. They can occur in the middle of the deep open ocean, far from any land or specific underwater topography. They are not part of a predictable swell pattern, but are statistical outliers that erupt from a seemingly random sea state, making them a far more insidious and terrifying threat to unsuspecting mariners. The shape of the waves is also different. The giant waves at Nazar and other big wave spots are breaking waves, spilling their energy forward as they roll towards the shore. While incredibly powerful, their behavior is relatively well understood. A rogue wave in the open ocean is often described as a moving wall of water or a hole in the sea. It can be exceptionally steep with a deep trough in front of it, and it may not break at all. A ship might fall into the deep trough and then be struck by the near vertical wall of water that follows, a force that can overwhelm even the largest vessels. So, while both types of waves represent the immense power of the ocean, they are born from different circumstances and pose different kinds of challenges. The waves at Nazar are a spectacular, geographically focused display of the ocean's energy, a challenge to be met by skilled athletes with extensive preparation. Rogue waves are the ocean's ambush predators, solitary, unexpected, and appearing where they are least expected. This distinction is vital for appreciating the unique danger that rogue waves represent, and why they have been the source of so much mystery and fear for those who travel the open seas. The study of rogue waves has moved from proving their existence to the critical challenge of forecasting them. For a sailor on the deck of a ship, even a few minutes of warning could be the difference between life and death. It could provide just enough time to change course, reduce speed, or brace for impact. Scientists are now turning to advanced technology, particularly artificial intelligence, to try and crack the code of these elusive phenomena. By feeding vast amounts of data into powerful computer systems, they hope to find the subtle patterns that might signal the birth of a rogue wave. Researchers have made promising progress in this area. At one university, a neural network was created and trained using data from hundreds of buoys that have been collecting wave information for years. This AI system learned to recognize the complex sea states that often precede the formation of a rogue wave. In a controlled, simulated environment, this system has shown the ability to predict the likelihood of a rogue wave appearing up to 5 minutes in advance. While this technology has not yet been tested in the chaotic conditions of the open ocean, it represents a significant leap forward and a ray of hope for maritime safety. Alongside prediction, research into rogue waves has also led to significant improvements in ship design. Understanding the immense focused forces these waves can exert has prompted engineers to build stronger, more resilient vessels. Modern ship hulls and superstructures are now designed and tested to withstand pressures that were once considered impossibly high. By acknowledging the reality of these 100-ton per square metre impacts, the maritime industry is better prepared to face them. This combination of smarter ship design and advanced forecasting technology forms a two-pronged approach to mitigating the threat. The ocean will always hold a certain mystery, and its power will always demand our respect. Rogue waves are a profound reminder of this. They are rare, with the chances of any single person experiencing one being incredibly slim, but their consequences can be absolute. They represent the extremes of the natural world, a place where physics, chance, and immense energy combine to create something truly awesome and terrifying. The ongoing work of scientists to understand and predict these giants is a testament to our drive to explore, to comprehend, and ultimately to safeguard our journey across the vast, beautiful, and sometimes monstrous oceans of our planet.